Hello students, welcome back to my channel Positron. Dear students, since last few days I was not feeling well, so I couldn't make the videos. Now again I'm in field. Dear students, today's topic is properties of matter in solid. And basically this chapter is basically called elasticity. Elasticity, right? So today's topic is properties of solid in matter, or it is also called elasticity. This chapter is very relevant in engineering. Right? Those who are the students of BTech mechanics, they have to study it at a very length, right? Dear students, in whole world, this is a properties of solid in matter, right? Means this chapter we are basically dedicated to the properties of solid. The matter is divided into five types: solid, liquid, gas, plasma, and Bose-Einstein condensation. Whether it is solid, liquid, or gas, no matter they are made of molecules. Molecules are further made of atoms, and atoms are and they are divided into electron, proton, and neutron. These are said to be the fundamental particles. Why do we call it fundamental particles? Because these are the particles which cannot be broken further. That is why it is called fundamental particle. Now, dear students, on the basis of elasticity, you can divide whole matter into two types. One is a plastic bodies and there is a elastic bodies. If a force is applied on the body, then that force used to do, either it changes the shape or the size, right? If a force is applied on the body and it changes the shape or size of the body, then such a force is called to be the deforming force. If a force is applied and it changes the shape or size of the body, this is said to be the deforming force. Dear students, there are the two kind of matter. Basically, can on the basis of elasticity, you can divide the matter into two types: elastic bodies and plastic bodies. Plastic bodies are what? If a force is applied, then its shape or size changes, and after the removal of the force, body do not come back to its original status. Such a body is called to be the plastic body. Again, listen. If a force is applied that changes the shape or size of the body, or both changes, and after the removal of the force, if body does not come back, does not regain its original status, then such a body is said to be the plastic body, right? And another one, if after the removal of the deforming force, body comes back to its original status, then it is called to be the elastic body. Nothing in this universe is a completely elastic. Nothing in this world there is 100% plastic body. Every body exists between the plastic and elastic body. After the removal of the force, if body regains its original status, then it is called to be the elastic body, and if body do not regain its original status, it is called to be the plastic body. Dear students, what I said, that the bodies are divided into two types: elastic and plastic bodies. After the removal of deforming force, if body regains its original status, then it is called to be the elastic body, and if body do not regain its original status, it is called to be the plastic body. Now, dear students, the force acting per unit area, the deforming force acting per unit area is said to be the stress. Now, from where does elastic property comes? This chapter is basically dedicated to the elastic properties of solid. Elastic property is what? If a deforming force is applied, then it might change the shape or size of the body, or both changes. after the removal of the force, if body regains its original status, it is called to be the elastic body. The deforming force per unit area is said to be the stress. Dear students, you must have studied pressure is what? Normal force acting per unit area, right? Pressure is defined as normal force acting per unit area is called to be the pressure. Now look here, the vector is divided by the vector, but the pressure is scalar quantity. Why do we call pressure as a scalar quantity? Simply because in the pressure direction is predefined. When you define the pressure, you say the normal force acting per unit area. Pressure is the direction is predefined. That is why pressure is a scalar quantity. But the stress, in the case of stress is not a scalar quantity. Stress is also when you define the stress, you say the force, the deforming force acting per unit area is called stress. Deforming force acting per unit area is called stress. But the direction is not predefined. The stress is a vector quantity. But better is to say, I'll say that stress is a tensor quantity. Tensor means a physical quantity, a vector physical quantity, or a quantity of higher rank vector. A quantity of higher rank vector is called to be the tensor. So pressure, undoubtedly pressure is a scalar quantity, but stress is a vector quantity, but is a vector of higher rank. That is why it is sometimes called tensor. Now, dear students, if you go through the elasticity, if you study the elasticity by NCERT, you will see that the atoms or molecules are associated with the spring. There is a figure made that the matter is made of molecules, and these molecules associated with the spring. They are not actually associated with the spring, but their behavior is they behave such that they are associated with each other. Each molecule of the solid is connected with each other as a spring, but it is not actually they are connected with the spring, but it is their behavior, right? They behave the elastic property. In order to make convenient for you the elastic property, you can say that the molecules in the solid are connected with each other, that they are connected with the spring with each other. Now, dear student, the we have to study. I defined elasticity and plasticity. Elastic property. In case of elastic, the example of elasticity, elastic material, steel is a better elastic material, right? The plastic plastic is a plastic material. Or the wet soil, if you make the bulb of wet soil, if you make a sphere of wet soil, it is undoubtedly plastic properties, right? So many examples are there of plastic properties, so many examples are there of elastic properties. It is said that prove that the steel is more elastic than rubber. Undoubtedly it's true that. Yet if a same amount of force is applied, then the rubber is more stressed, but it is the steel which is more elastic than the rubber, because after the removal of the force, the steel will gain exactly or more approximately close to its original status. But after the removal of the force, the rubber cannot come back to its original status. There is some change left even after the removal of the force. Now, dear student, further we have to define the elasticity. Now we are going through a topic that is called strain, right? Whole elasticity is the study of stress and strain. Now, strain is what? Just I have said that if a force is applied, either it changes the shape or the size, right? If a force is applied, either it changes the shape or size. In the change of the shape and size, the strain is divided on the basis of change in the shape or size. The strain is divided into three types. First one is a longitudinal strain. If a deforming force is applied, then within the elastic limit, always in this chapter we will use always the within the elastic limit, means that force, the deforming force should not cross a limit. The force applied on the body should be within a limit, and that is said to be the elastic limit. So longitudinal or linear strain. What is this? Longitudinal or linear strain. Dear students, longitudinal or linear strain. What is? If the deforming force is applied on a thin wire like this is a thin wire hanged with the rigid support, and this is a weight is applied here, right? Then what happens? The length of this wire changes, or this wire is elongated, or this wire is stressed because of this force applied, because of the weight applied at the end of the wire. Now, longitudinal strain or linear strain is what? Within the elastic limit, it is the ratio of change in length and original length. Within the elastic limit, linear or longitudinal strain is a within the elastic limit, it is the ratio of change in length and original length. Let the original length is a L. Now look here. If dimensionally you will check, dear students, this is length. So both has the numerator and denominator, both has the dimension of length. So the strain is a dimensionless quantity. Every strain is a dimensionless quantity. Now second one is a what? First one was the longitudinal strain or linear strain, right? Second one is a volume strain. Dear student, longitudinal strain, when it is applied in the case of thin wire, when weight is applied, or when it is stressed or weight is applied at the second end of the wire, then it is a linear strain. Is a ratio of change in length and original length is said to be the linear strain. Now volume strain is what? Let a solid cube is kept and it is compressed. A pressure of very high Pascal is applied to it. Then what happens? Its volume changes. Now the volume strain is what? Within the elastic limit, the volume strain is defined as within the elastic limit, ratio of change in volume and original volume. Within the elastic limit, ratio of change in volume and original volume is said to be this is a volume strain. Within the elastic limit, ratio of change in volume and original volume is said to be the volume strain. And third one is a dear student, shearing strain. Just at the beginning of topic, I have discussed with you a force applied on the body which either changes the shape or size of the body. Now that these two stress, we are changing the size of the body. Now this shearing strain, if a force is applied on the body such that it changes the shape of the body, yet size remains constant. If a force is applied such that it changes the shape of the body, yet the size remains constant. I am giving a very good example. The room in which you are sitting and watching my videos, look here, it has the 6 faces. At the upper face, lower face is filled. Let the lower face, the ground is fixed on which I am standing and delivering my lecture. At the top, the roof I am talking, and a tangential force is applied along the roof. Then what happens? Look here, the initial condition of the wall is this. If a tangential force or stress is applied, then what happens? Let it is A, it is B initially, and it is C, it is D. A will come to here A dash, and B will move to here B dash, right? And this phi is the angle of shear, or this phi. In this case, we will say that the wall has sheared by an angle phi. This is the shearing strain we are talking about. The two strains were connected with the change in the size, and third one is connected with the change of the shape. If that a tangential force is applied on the roof of the room in which you are sitting, then the two walls which are supporting the roof will just bend like this, and the angle by which they bend is said to be the angle of shear, or shearing angle, or shearing strain. Now, dear students, as soon as the tangential force is applied, A goes to A dash, B goes to B dash. This phi is the angle of shear, and you can say, let each side of the wall is capital L, and this is the AA dash, that is equal to BB dash, and that is equal to change in length L. Then phi, if angle is a very small, you know, sin theta equal theta, tan theta approximately equal theta, you might write theta, you can write that is tan phi, that is equal to change this perpendicular upon base L upon L. So angle of shear phi becomes small l upon capital L. Dear student, the three strains we discussed with you, I discussed with you all the three strains. First one was the linear strain, that is the ratio of change in length and original length. Second one was the volume strain, that is the ratio of change in volume and original volume within the elastic limit. And third one was the shearing strain. Shearing strain is the angle phi by which the wall shear, that is a phi, that is equal to phi is equal to small l upon L. That is, if a tangential stress is applied, then shape of the body, here the tangential stress, tangential force is applied, A goes to move to A dash, B move to B dash. This wall bends by an angle phi. This angle phi is said to be the angle of shear, or phi is equal to, approximately you might write tan phi, that is equal to small l upon L. Dear student, on the basis of these three strains, the stress also can be divided into three types. Corresponding to longitudinal strain or linear strain, there is a linear stress or longitudinal stress. Corresponding to volume strain, there is a normal stress, and corresponding to shearing strain, there is a shearing stress. Regarding to three strains, the stress also can be divided into three types. The longitudinal strain or linear strain correspond to linear stress, and linear stress is what? That is a force divided by area. Force is a weight here mg, and A is a what? A is the area of cross section of this wire. A is what? Cross sectional area of the wire on which weight has been hanged. Let small r is the radius of this wire. Then force mg, force is actually the mg, that is weight hanging, and A is the pi r square. So this is the linear stress. Corresponding to volume stress means we are talking about that which stress will produce these strains. We are talking about that which stress is capable of producing linear strain, producing volume strain, and which stress will produce the shearing strain. Now, dear student, volume strain, I have said that a block, a cube we have considered, and high pressure is applied on it. So it is called normal stress, and that is expressed by P. And third one is a just going to remove all this. Now, dear students, what I was discussing with you are the linear strain. Linear strain that is produced by linear stress. Linear stress is what? That is a force upon area. This was your wire and a weight was hanging. Small r was the radius cross section of this wire. So F is equal to mg here and area is a pi r square. So this is linear stress produces linear strain, and corresponding to linear stress and linear strain, the constant of elasticity associated is called to be the Young modulus. There are the four modulus of elasticity. One is a Young modulus, and there is a that is bulk modulus, modulus of rigidity, and Poisson's ratio. They are the four elastic constants we have to study in this topic. First one is a Young modulus, second one is a bulk modulus, third one is a modulus of elasticity, and fourth one is a Poisson's ratio. Dear students, I have said that linear stress produces the linear strain, and linear stress is a force upon area. Area is a cross-sectional area of the wire from which the weight has been hanged. Force is the weight hanging, that is a force mg, and area is a pi r square. R is the radius of cross-section of wire. So area of the cross-section of wire is a pi r square. So linear stress is equal to mg upon pi r square. Dear students, now the dimension of the stress is the dimension of pressure, because pressure is a force per unit area. In the same way, stress is also the force per unit area, but the difference between them is the pressure is a scalar quantity, but the stress is not a scalar quantity. It is a quantity of higher rank vector, right? It is a vector of higher rank. Sometimes it is also called tensor. Now, dear students, if you find out the dimension of any stress, this is mg upon pi r square, force upon area. Force is a, for any stress, dimension will be, force is a, that is mlt minus 2, over area is a L square, that is a, that works out to be ml minus 1t minus 2. Now, dear students, what we have to do, that corresponding to linear stress and linear strain, the constant of elasticity associated is called Young's modulus, and it is represented by Y. Within the elastic limit, Young's modulus is the ratio of, within the elastic limit, Young's modulus is the ratio of linear stress or longitudinal stress and linear strain. Dear students, Young's modulus is what? That is the constant of elasticity associated with the linear stress and linear strain is Young's modulus. Within the elastic limit, Young's modulus is the ratio of linear or longitudinal linear stress and linear strain. Within the elastic limit, Young's modulus is the ratio of linear stress and longitudinal linear strain. Now, look here, Y is equal to, longitudinal stress is a force upon area, linear strain is a change in length upon original length, Ry is equal to, F is a mg, area is a pi r square over small l upon capital L. Or dear students, you might write that Y is equal to mg capital L will be the part of numerator, and all these pi r square L, that is a part of denominator. Now dear students, look here. What I have said, that the dimension of pressure and dimension of stress is similar. The difference between these two, the pressure is a scalar quantity and stress is a vector of higher rank. Now dear students, Young modulus is the ratio of longitudinal linear stress and linear strain. Strain is a dimensionless quantity. So Young modulus has the dimension of stress or dimension of pressure, and dimension of pressure is ml minus 1 t minus 2. So Young modulus has the dimension ml minus 1 t minus 2, and unit will be what? Longitudinal stress, that is a force upon area. It is a dimensionless or unitless quantity. So F upon A means Newton per meter square, right? Young modulus has the dimension of stress or dimension of pressure. The dimension of Young modulus is similar to dimension of pressure or dimension of stress, and that works out to be ml minus 1 t minus 2. And the unit you can write, it is a dimensionless, unitless, so it is F upon A. Newton per meter square is the unit of Young modulus. Now dear students, let's come back to second one. That is a this whole chapter I am dividing into parts. This is the part on that we will talk about in this part we will talk about the 4 elastic constants. In part 2 we will talk about the different column, pillars, beam, stanchion, like all that, the uses, the applications of the elastic constants and the behavior of stress wire. All that we will study in second part. Now dear students, the second one is a first elastic constant we discussed was Young modulus, and second one is a bulk modulus. We denote it by capital case. Different books may denote by different words, no matter. Bulk modulus. Dear students, let it is a cubic block, right? And pressure of very high, a normal pressure of very high Pascal is applied to it. Initial volume was capital V, the change in volume is small v. Now what happens? Bulk modulus is, how will you define bulk modulus is? That is, within the elastic limit, it is the ratio of normal stress and volume strain. Every elastic constant, undoubtedly, definitely it is the ratio of stress and strain. Regarding to a particular elastic constant, you must should be familiar, you must should know that what kind of stress and strain we are considering for a particular elastic constant. So bulk modulus is the ratio of normal stress within the elastic limit. Bulk modulus is defined as a ratio of normal stress and volume strain. Within the elastic limit, bulk modulus is defined as the ratio of normal stress and volume strain. Now dear students, look here. R capital K is equal to normal stress is what? That is a small p, just denoted by small p, represented by small p, and the volume strain is, that is change in volume divided by original volume, and I am putting here negative. Negative why? Simply, if pressure is increased, volume decreases. That this represents that if the normal pressure is increased, the volume of the block decreases, or K is equal to minus P capital V upon small v. Dear students, again if you want to find out the dimension or the unit of this bulk modulus, this is dimensionless quantity, volume divided by volume, change in volume divided by original volume. So it is a unitless and dimensionless quantity. So the dimension or unit of capital K is a unit and dimension of P, and P is undoubtedly Newton per meter square. Our dimension is denoted by ml minus 1 T minus 2. So in this way we came to the bulk modulus, and third one is a dear students, third one is a that is a modulus of rigidity. Modulus of rigidity. Third one is a modulus of rigidity. First one was Young's modulus, second one was bulk modulus, and third one is a modulus of rigidity. It is denoted by eta. Dear students, already I have given you the example that one face of the room I have considered, one wall of the room I have considered, the room in which you are sitting and watching my videos, consider just one wall like this wall, okay? The ground on which I am just standing and delivering my lecture, and on the roof a tangential force, a tangential stress, might you better is to call it tangential stress, is applied. Now this is A, B, C, D. A goes to A dash in this way, B goes to B dash in this way. Now the wall bend, the supporting wall on which the roof is, this wall bend by an angle phi when a tangential stress is applied on the roof, and this angle is an angle of, called to be the angle of shear. This is the change in length L, and this is the original length capital L. Now I have said that angle of shear, that is a phi is equal to tan phi, approximately equal to phi, that is equal to change in length upon original length. You must know for a very small angle sin theta is equal to theta and tan theta is equal to theta. Mathematics, simple mathematics. Now dear student, modulus of rigidity highly defined. The modulus of rigidity eta, within the elastic limit, it is the ratio of tangential stress and shearing stress. Within the elastic limit, modulus of rigidity is the ratio of tangential stress and shearing. Tangential stress and shearing strength. Now dear students, what happened? Tangential stress is what? Within the elastic limit, it is the ratio of tangential stress and volume and shearing stress. Tangential stress is the force applied, tangential force applied, and area is what? The area on which the tangential force, in this case I am talking about the area of the roof, that is the area of the ceiling. Upon shearing strength is the angle by which the supporting wall bended, right? This is the phi, or eta is equal to F upon A phi, or you also can write F upon A. This can be, phi can be replaced by small l upon L. So that is R eta is equal to, this L will be part of numerator like this, and now this is the modulus of rigidity. Now dear students, again the dimension of modulus of rigidity, this is the angle. Angle is a dimensionless, unitless. A unit is a radian, but the dimensionless quantity. So eta has the dimension of F upon A, that is a pressure, ml minus 1 T minus 2, and the unit of eta modulus of rigidity is again and again Newton per meter square. Dear students, Young modulus is, whether it is applicable to all form of solids? No. Young modulus is all form of matter? No. Young modulus is applicable only to the solids. Bulk modulus is applicable to the solid, liquid and gas in all the form, because that is a ratio of normal stress and volume strength. Volume can be changed in solid, liquid and gas. So bulk modulus is applicable to all the three form of matter, solid, liquid and gas. And modulus of rigidity, the third one, modulus of rigidity, this is the applicable only to the solids. So Young modulus and modulus of rigidity are applicable only to the solids, whereas bulk modulus is applicable to the solid, liquid and gas. Yet this chapter is dedicated to the properties of matter in solids, right? Now, fourth elastic constant that I have to discuss with you all, that is a fourth elastic constant that I have to discuss with you all. This is, dear students, it is a part 1. This whole chapter I have divided into the 2 parts. The first part is containing Young modulus, bulk modulus, modulus of rigidity and Poisson's ratio, all the elastic constant. What is the elastic property? What are the plastic properties? And second part, we will discuss about the elastic behavior of the wire, applications of these elastic constants. Why do we study the elasticity? That we all study in that part. Now, dear students, the fourth one, the fourth elastic constant, that is said to be the Poisson's ratio. Poisson's ratio. Within the elastic limit, Poisson's ratio within the elastic limit, Poisson's ratio sigma is the ratio of lateral strain and linear strain. Lateral strain and linear strain. Poisson's ratio within the elastic limit, Poisson's ratio is the ratio of lateral strain and linear strain. Lateral strain is what? This is the wire, dear student, this is the wire, and initial length is capital L and supported from a rigid wall, right? And here a weight has been hanged, and this weight is a mg, right? Let the change in length is small m. Initial diameter was capital D and the change in diameter is small d. Dear student, if a weight is hanged, weight is supported by the wire, then wire will be stretched. The length of the wire increases, in result of which its diameter decreases. So, lateral strain is what? Let the L is the original length of the wire, and that if you hang the weight, if you apply the weight, the change, increase in the length of wire is a small l, whereas the initial diameter was capital D, and change in the diameter because diameter contract. Diameter decreases if the length increases, and the change in diameter is a small d. Then linear strain, undoubtedly, just I have discussed with you all that change in length and original ratio of change in length and original length is the linear strain, whereas lateral strain is what? That is the ratio of change in diameter and original diameter. So sigma is equal to, dear student, lateral strain is the change in diameter upon original diameter. Linear strain, that is change in length and original length. Change in length and original length. And negative, I'm putting a negative sign. Why? If the length increases, diameter decreases. That is why both are just reverse to each other. Now, you might write like this, minus, dear students, capital L will come here, capital D will be here, and now here it is small d, small l here. You can write this, sigma is equal to minus L upon D. Small d is the change in diameter. That also can be written as dd. Capital D is the original diameter, then dd is this is change in the diameter, and small l is the change in length. That also can be written as dl. dl is the change in capital L. So this is the Poisson's ratio. Sigma is equal to capital L upon D, dd upon dl. This is also applicable to the solids and gases, solids and liquids also, right? So in this way, dear students, I have discussed all the 4 elastic constants with you all, that is a Young modulus, bulk modulus, modulus of rigidity and Poisson's ratio. I hope my videos are going to be beneficial to you. If you think that my videos are effective to you or beneficial, make your study convenient, then please and please requesting you all to please and please share my videos, comment on my videos, and must put the bell icons so that you might be notified about my new videos. Meet you in next video. Thank you.